So today we are going to do a lab called Numerical Modeling of Steady-State Seepage with SEEP-W, lab number 7. Steady-state seepage means the water is flowing through the soil. However, the head difference is constant. So a good example would be constant head fall permeability test, where we had a soil sample and we created a head difference between upstream and downstream, and the water was flowing through the soil sample under the constant head difference. So that's a good example of one-dimensional steady-state seepage flow through soil. So today we are going to look at how to analyze it in two dimension. And one of the methods to do that is finite element method. And for that we are going to use a computer program called SEEP-W, which is used by quite a few consulting firms. And it is important that you do this lab because lab number 8 is going to require you to use SEEP-W, and then your class project is also going to use SEEP-W quite heavily. So the Laplace equation to describe steady state seepage flow in two dimension can be written as where Kx and Kz are hydraulic conductivities or permeabilities of soil in x and z direction, or horizontal and vertical direction. H is the total head at any point, which is dependent on its x and z coordinates, and that's why it's a partial differential equation. And Laplace equation still assumes that Darcy's law is valid and soil is homogeneous and so on, that you have seen in CE 180. So on top of that, if we assume the soil to be isotropic, that is Kx equal to Kz, it simplifies the Laplace equation. Okay. And that's what we are going to use for our homework today. So here is an example of an earth dam, which is a good two-dimensional problem to study. So the dam is quite long. So if you look at a cross section of the dam here in the middle, or a few meters or feet away from it, all these cross sections are going to behave quite similarly. So we can draw the cross section of a dam like this. Let's assume that it's founded on solid bedrock, which is impermeable, so the water cannot pass through it. Oftentimes there is some kind of drainage provided, so the water goes towards that. And then we have high water condition. And under this, if we wanted to study how the water may flow through the dam, this makes a good two-dimensional steady state seepage problem, and the water is going to pass through the soil, something like this most likely. And this is a good 2D representation of water through embankment dam. So the next example we are going to look at is an example of a coffer dam. So coffer dam is a structure where you can see there is a water here, so some kind of a river or lake or something like that. And if you want to construct something that in the middle of water, oftentimes a structure is constructed to create that space, and then you use some pumps or something like that to take the water out of it and to keep it dry, and then the dry portion then can be used for construction. So if you can see, this particular structure is surrounded by water, and let's say if you took this cross section or that cross section, they both are going to behave very similar. So a way to construct it may be that there is going to be a soil layer, and in that we are going to have these what are called as sheet pile walls. Okay, and there is going to be water on both sides. Okay, so there will be some kind of a pump that will operate here to keep this draining. So that way we can assume that the water level inside is about close to the ground surface. So the water in this case is going to flow from outside to inside. Okay. And this again is a good representation of two-dimensional steady state seepage. And once again, we can use the Laplace equation to solve this situation. In order to solve this Laplace equation, there are three types of solutions. One is considering some kind of a physical model that we are going to do in lab number 8, a graphical solution that you studied in CE 180 where you draw hand-drawn flow nets, and the third is numerical solution. And within that there is a finite element simulation and finite difference. And the program SEEP-W uses finite element simulation. So on the left here we have a graphical solution that you have studied in CE 180 where we try to draw a square flow net where we have flow lines like these, and then we have equipotential lines. Right? These are equipotential lines. And the same is on the right for the same kind of a hydraulic structure, but in this case it is SEEP-W solution. So we are going to learn how to set up this problem in SEEP-W and solve it. So the problem we are going to consider today is that of a hydraulic structure under steady state seepage condition. So let's say we have a bed of soil sitting on some kind of an impermeable bedrock, and we want to build a reservoir, and because of that we are going to build a small concrete dam and hold water behind it. Okay, so if we construct a dam just like this, what's going to happen is water is going to flow directly under this, and if it moves rather too quickly, it's going to start bringing the soil particles with it, and eventually more and more water will come out, and something that is called as piping will happen, basically creating a conduit for water, and the hydraulic structure will fail. So this gradient here that the water comes out with is called exit gradient, and usually one tries to maintain it below about 0.25 or 0.3. And in order to do that, one way one can do is build some kind of a cutoff to prolong the path of water. So instead of going this way, the water will have to go around it, and that way the exit gradient will be reduced. So exit gradient, so factor of safety against exit gradient is critical gradient of the soil divided by exit gradient, and your notes have additional information on critical gradient, which happens to be about 1.0. So that's why in order to maintain a factor of safety of about 4, which is preferred for a hydraulic structure, you need to make the exit gradient less than 0.25 or so. So that would be the goal. This is a representation of that structure. Although this soil goes much further, there is no need to make the model too big. So we have a water reservoir that's about 3 meters high. We have a concrete structure with a cutoff, and we have this soil. And on the downstream side, we are going to assume that the water level is at the top of the ground surface. So this is called upstream, this is called downstream. Um, so we are going to build a model that is going to take only, for the most part, this part. So we technically need to model only the soil. And so we need coordinates to take 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if we draw this, there are these points where we have the hydraulic structure. So this one is going to have certain water total head, and this one is also going to have a certain water head, total head for downstream and for upstream. And at all these other boundaries, the water cannot go across it. So the program will assume that is the case. So essentially water is going to go from this blue part to that blue part around the structure. So the program will solve this problem by dividing the soil layer into a bunch of elements, and that is why it is called as finite element program. So the finite element program will require one to create the soil domain and find its boundary conditions as shown here in blue and black. And your goal here is to also calculate exit gradient. So you will be calculating flow under the dam and exit gradient. And we are going to create multiple models for z equal to 1, 2, 3, and 4 meters, and plot two plots of z versus flow rate under the dam, and z, or the depth of cutoff, versus the exit gradient. Okay, to see how increasing the depth of the cutoff here is going to affect the water amount of water that's going to flow under the dam and the exit gradient.